Perdón, Claudette, siempre te tira, ¿verdad? Dígame otra vez tu pregunta, ya me olvidé.
It was about using this methodology, but
Ah,
with
ya,
another
ok,
element and
sí,
another spectrum of light.
sí, sí, pudimos, aunque como para estos tipos de moléculas basado en carbono o con silicio, necesitamos enlaces covalentes y casi todos los enlaces covalentes más o menos tienen la energía en este rango, en el VC, en el 210 a 285. Entonces, aunque estamos hablando de silicio, yo creo que también tenemos que estar pensando en este rango de longitud de onda. Puede ser, pero también eso es muy especulativa. Puede ser que hay vida basado o sistemas disipativas basado en los enlaces de Van der Waals, por ejemplo, ¿no? Que son más débiles. Y esto pudiera ser invisible, pero el hecho que no hemos encontrado en la Tierra ese tipo de vida, o por lo menos no hemos reconocido, quizás nada más también son pigmentos en el visible, ¿no? Que en donde están los enlaces, la fuerte del enlace para los enlaces de Van der Waals, ¿no? Entonces, yo creo que si es enlaces covalentes, tendría que estar en el VC, porque necesitas esta energía para poder romper y formar otros enlaces. Pero sí pudimos, hay tantas cosas que pudimos hacer, ¿no? A partir de estos ideas. Pero yo creo que antes de animarnos tanto, tenemos que primero convencer a los demás de que este sí pudiera ser una buena explicación del origen de la vida, ¿no? Entonces hay muchas cosas, si quieren ustedes, ya cuando yo no estoy en esta tierra, ustedes pueden seguir en todos estos temas. Yo creo que será un muy amplio espectro de temas que podemos estar estudiando, basado en disipación. También yo creo que la disipación no solamente tiene juego en el origen de la vida, pero también en otros problemas todavía no bien resueltos, como por ejemplo, sabiendo, conociendo el origen de la energía oscura o la materia oscura, la estructuración de las galaxias, por ejemplo. Ese también es un proceso disipativo, pero no tanto en energía, sino en momento angular. Entonces hay un montón de cosas, un montón de cosas que se pueden estudiar a partir de este, esta área, ¿no? De termodinámica fuera de equilibrio. Ok, entonces vamos al otro, la siguiente. Bueno, so here, this is the same graph that I've showed before, is that it is a small peak that we need in the UVC to be able to form dissipatively structure these molecules based on carbon. And we have to be shielded on the surface of the planet from wavelengths which are below about 210. And on Earth, it's supposed that hydrogen sulfide, which comes from volcanoes, and carbon dioxide, which is also a gas from volcano, that these are shielding these lower or these shorter wavelength photons, which are dangerous because they cause ionization. However, they are needed in the upper atmosphere to produce, for example, hydrogen cyanide. So in the upper atmosphere, we can have dissipative structuring of hydrogen cyanide with shorter wavelength photons. And we also have these aldehydes here, but this region, like from 285 to 310, it's not very dangerous for life. We could also have, this was not shielded, for example, with these aldehydes, and we could have had this light occurring and still be forming molecules. And this other light also in the visible is not dangerous. But if we only had light in the visible, then we could not form these molecules because we need this UVC range to form these covalent, to change the covalent bonding in the molecules. So, and we showed this graph also of the molecules. These are the basic fundamental molecules of life: the nucleic acids, amino acids, fatty acids, sugars, vitamins, coenzymes, and cofactors. Many of them, not all of them, but many of them, not only absorb very strongly, but also have this conical intersection, which means that they are designed to dissipate. They absorb the energy of the photon and they dissipate it to the ground state. That is, they convert it into infrared light in about 10 to the minus 12 seconds, so in a picosecond, very rapidly. Okay. So now if we look at these other stars, what does their spectra look like? So this line here is M-type star. This is the M star, the black line. These are the stars which are most frequent in our galaxy. And probably in all of the galaxies in the universe. And if this M-type star doesn't have any light in this UVC range here, so this is the same, this is what the spectrum of these different stars would look like at the surface of the atmosphere, at the top of the atmosphere. Okay. So this is just the black body spectrums for the different temperatures stars. So this is the A-type star, which is one of the hottest types of stars. So it's producing a lot of light in the UVC range. So this here is what the spectrum would look like for a planet which has the same type of gases as Earth had at the beginning of life. So if it had carbon dioxide and hydrogen sulfide, and it had some aldehydes like formaldehyde, then if it had the same pressure as we assumed for the Earth, this planet, depending on its star, would have these spectrums. And we see, for example, for the A-type star that we have a lot of light in this UVC range. So that would imply that we would have a lot of dissipative structuring going on. But you also see that we have some light here in this shorter wavelength range. This is what I call the medium UVC range here. This is an amplification of this spectrum. And this is dangerous to carbon covalent bonding because it causes ionization. So it would be rather difficult because we would have production of the molecules and then destruction of the molecules because of this medium or middle UVC wavelength region, which is coming on the A-type stars. But we can have this K, is it K or H? No, it's F-type star, sorry, F-type star. And the K-type stars, both the F-type star and the K-type star do have some UVC range and very little, well, the F-type star still has some middle UVC range, or it could be causing damage. But it's basically only these three types of stars. So we have the K, the G, and the F-type stars that could give us this particular spectrum, which we need in order to produce the molecules, but not destroy them at the same time. Okay. So it's very unlikely that we're going to have life found on M-type stars, at least life like we know it. Ok, entonces hay algunas preguntas sobre esos son los espectros que encuentras en la alta atmósfera. Estamos asumiendo que tenemos un planeta como la Tierra, que tenía las mismas gases que tenía la Tierra en principio, como dióxido de carbono, como hydrogen sulfide, como aldehydes, aldehídos, creo que se dicen, que tuvimos estos gases en la atmósfera del planeta, pero alrededor de distintas estrellas, ¿no? Ese es el caso de la estrella tipo A. En este caso es peligroso porque tenemos un región en donde la luz que está llegando a la superficie es en el medio rango de UVC, que tiene energía suficiente para ionizar y causar daño. Entonces, quizás en estos tipos de estrellas no vamos a tener posibilidad de luz, estructuración disipativa con esta luz, porque se destruye rápidamente. Y solamente el K y el G y el F son los únicos estrellas que pudimos tener este tipo de estructuración disipativa con carbón. Okay, Claudette, you have a question? I know you like to speak English, so that's great.
But I speak very bad English.
That doesn't matter. It doesn't matter. You're getting better. That's the main point that you're trying.
Okay, so if I understand, the colors represent the different type of stars that
Yes,
we saw before,
right.
and
So
the black color, what type of star it was?
is the black color is the M-type star. So it's the red dwarf. Let me go back. It's this star, this M-type star.
Okay.
It's the most common star in the universe, but it only produces in the infrared. So it's very unlikely that we would get dissipative structuring of carbon-based, covalent-based molecules with the M-type star. And these are the other ones. I can't read them either from here. Let me see. This is K-type star. No, this is a K star. This is a Leo. This is also an M-type star. I just put it in because it's another star which does have a little bit of light in the ultraviolet, and which many astronomers or astrobiologists are studying, because they are looking for life on these type of stars, but I don't think they will find it.
Maybe that's the reason.
Yeah, so we should actually write the paper. As I mentioned, that we suggested this in another paper, but we didn't develop it. We have to really develop it with all these graphs and arguments. So that could be, if Andres, for example, is interested in doing that for his thesis project, that could be a nice thesis project.
Sí, suena interesante.
Aha. Possibility of finding life on other stars, no? Okay.
Sí, yo de chico, cuando me empecé a interesar la física, compré un libro de divulgación
Ajá.
que mencionaba la astrobiología, y pues en ese entonces a mí me sonó muy loco, ¿no? Todo eso de buscar vida.
Sí, la verdad es mucha especulación todavía, pero poco a poco tenemos que empezar con la especulación y ponerlo a vista a la comunidad científica y esperar sus críticas y así aprender y andar mejorando. Esa es la única manera, todo es especulativa, pero alguien tiene que empezar. Bueno, sí es una cosa interesante que la humanidad piensa que es interesante descubrir que hay vida en otros planetas. Algunos no quisieran saber, pero yo creo que es parte de la cultura, ¿no? Que tenemos este interés inherente en saber si estamos solo en el universo. Muchos que son muy creyentes no les van a gustar. Claro que se pueden adaptar la religión también a otras posibilidades que está adaptando. Por lo menos la religión cristiana está adaptando a los descubrimientos científicos, pero hay un grupo de gente que están opuestos totalmente contra esto de búsqueda, ¿no? no tanto porque tienen miedo de que encontramos algo, sino que está en contradicción a sus enseñanzas desde la juventud. Entonces, por algunos es muy pesado esto, ¿no? Que no creen que es válida. Pero yo creo que la humanidad y cada vez más estamos interesados en estas preguntas, ¿no? De si estamos solos en el universo y cómo se forma la vida, ¿no? ¿Por qué no la vida? Andrés, ¿tú tienes una pregunta específica de esta gráfica? ¿Sí entendiste? ¿O hay algo que no está muy claro?
I think that it's in order for the moment.
No, de esto todo bien. Es un
Ok.
poco como la duda que tenía al principio de
Ok,
qué buscamos observar, ¿no? En los espectros de los planetas que nos interesan.
ok. Sí, sí está muy especulativa y quizás uno pudiera decir que es un poco lejos de la ciencia común hoy en día, ¿no? Pero alguien tiene que empezar. Bueno, entonces nada más para resumir, we need light in the short wavelength UVC range on the upper atmosphere, not on the surface of the planet. Because if it was on the surface of the planet, it would destroy these carbon-based molecules, which are the fundamental molecules of life. But we need it in the upper atmosphere to produce, for example, hydrogen cyanide. Hydrogen cyanide can be produced by absorbing a photon or nitrogen and causing it to disintegrate into a nitrogen atom. And then this nitrogen atom combines with methane, and that produces hydrogen cyanide. Okay, and so this hydrogen cyanide we know, or at least Claudette knows, that we need it to produce these DNA bases like adenine and guanine, and the other ones also. So we need this light in the upper atmosphere in short wavelength to produce hydrogen cyanide. And maybe also we need this light to produce ribose, which is a sugar. There are other ways of producing ribose sugar on the surface with UVC light in the range that was arriving at the Earth at that time. So we're looking at that also. But one way of producing ribose is for water on formaldehyde. This is formaldehyde with a photon of 122 nanometers, and then we can produce ribose. So this is also like dissipative structuring of ribose at 122 nanometers in the upper atmosphere. And for that, we need this short wavelength light. Now on the surface, we need the long wavelength UVC light to produce these bases, like adenine in this case. We also need this long wavelength UVC light to produce what is called phosphorylation. Phosphorylation is the attachment of these phosphate groups. There are 3 phosphate groups which attach to the ribose, which attaches to the base, the DNA base, or the RNA base. And these phosphate groups give the system energy. So this is like, for example, adenine triphosphate. Tri because the 3 of them, 1, 2, 3 phosphate groups. And this is now used by life as the fundamental energy supply. So life produces this triphosphate now through charge gradients across the membranes of the cells. But at the beginning of life, they could have been produced by light, because it has been shown in the laboratory that if you have phosphates around and you have this nucleoside, so the base with the sugar, then you can phosphorylate the nucleoside to produce this nucleotide, it's called. And with these 3 phosphate groups, they can join together because 2 of them drop off, and that gives you enough energy to form the the covalent bonding with another base, which has another 3 phosphates. So anyway, for phosphorylation, you need long wavelength UVC light. And as I mentioned in the previous talk, for reproducing DNA to a physical mechanism, which doesn't depend on enzymes, we also need this long wavelength UVC light. And we need the temperature to decrease on the Earth's surface, as I mentioned, over time. Okay, and this is the UV tar mechanism. For proliferation, we also need UVC light. Remember, I gave this example of how DNA is proliferated, that means multiplied, over the surface of the Earth, because it uses the single strands as a template for double strand at night. No? So this is like an autocatalytic system. This single strand is acting as a catalyst to form another strand. And that gives rise to proliferation. And we find that also in the production of adenine, where we have some of these precursor molecules act as a catalyst for the formation, for example, of cis-DAM or trans-DAM. So this is proliferation, and for that we need this long wavelength UVC light. And also for homochirality, we didn't really talk about this, but also the interesting thing is that the greatest amount of chirality, which is found on the ocean surface. And it's produced by light, which is first reflected of whatever can be even the water molecule. We get a single reflection, we get polarization in a plane polarized light. And then if it internally reflects at the ocean surface, then we get circularly polarized light. And circularly polarized light can give a difference in right-handed or left-handed production, because light is circularly polarized right-handedly in the afternoon and left-handedly circularly polarized in the morning. So it looks symmetric in that you wouldn't get a difference. But there is a difference because the temperature of the ocean surface is different. In the afternoon, it's warmer. So if you have a warmer ocean surface, you can get more denaturing. So you get a little bit more denaturing of right-handed circularly polarized light over circularly polarized DNA. Okay, so this mechanism of homochirality, we have also published it, but it's also based on long wavelength UVC light. And if you look at DNA, there is what is called dichroism. There's a difference between the absorption of left-handed and right-handed circularly polarized light. And that helps us with this mechanism to select only certain chirality of the molecules of light. And we also need it for evolution, because as I mentioned in the previous talk, for example, if we have the amino acids like tryptophan, which also absorbs in the UVC range, but it doesn't have a conical intersection. Well, it can attach with DNA bases and pass its excitation energy onto the DNA base, which does have a conical intersection. And so the whole system is a greater dissipating system than the components separately, because the components separately would mean tryptophan would excite and it would fluoresce, would give a light, which is not heat, which is not in the infrared. So it doesn't dissipate as much as when it's connected with DNA, and it uses the conical intersection of DNA to dissipate that light into heat. So this is evolution. This is complexation of molecules. Two molecules coming together and make a greater dissipating system. And for this, we also need long wavelength ultraviolet light in the UVC. But we don't need medium range ultraviolet light on the surface of Earth in the UVC range, because this causes ionization. So we lose an electron and then we start destroying the molecules of life. Okay, so that's a basic summary of what are the kinds of light that we need for this dissipative structure. We need short wavelength UVC light in the upper atmosphere to produce hydrogen cyanide and maybe to produce ribose. And we need long wavelength light to produce phosphorylation and long wavelength UVC light to produce this proliferation or this replication of DNA, and long wavelength light to, well, for this process to occur, and for the production of homochirality of life and for evolution. But we don't need any medium wavelength UVC light because this light is dangerous because of its ionization potential. Okay, so any questions, preguntas, Claudette, sobre este acetato?
I don't know.
No? Okay, you want to think about it? I'll give Ivan a chance. And you let us know when you have a question. Ivan?
No creo que no.
No? Okay, Andres? No? Okay, Claudette, if you have a question, otherwise we'll go on to the next slide. Yeah, we're coming to the end now.
I think
We
that
get,
it's okay for the moment.
okay. Okay, if we get thrown off, then this is going to be the last session, okay? So now what I've done now is for each type of star, and this is its surface temperature of these stars. Okay, so the M-type, the red stars have a surface temperature of 3000 K, so that gives rise to this black body spectrum, which is in the infrared. And the G-type stars, 5840 Kelvin. And I've calculated the distance that we need the planet to be from the star in order for water to be in its liquid form, okay? So for the sun, in that case, we need a distance of 1 astronomical unit, the distance of the Earth from the sun. There we know that we have water in its liquid state. For an M-type star, we have to be very close to the M-type star, 0.16 astronomical units, just to have water in a liquid state, because the M-type star gives out very little total energy. These are the total energies that are given out by the star at these distances. So these are more or less the same. They were adjusted to be more or less the same. And these are the distances at which give the total flux of radiation to be about the same, so that we get liquid water on the surface of the planet. And at those distances, these are the different fluxes of the long wavelength, long range UVC wavelength. Okay, this is what is the good light, the good UVC light for the origin of life. And this is the middle range. This is the bad light. This is the short wavelength range, which is good light as long as it only arrives at the upper atmosphere to produce hydrogen cyanide and to produce ribose. Okay, so so this is the long wavelength range we needed for dissipative destruction, phosphorylation, denaturing, proliferation, homochirality, and evolution. And the M-type is dangerous because it ionizes. And this is a case, for example, I think this is adenine or guanine. Oh no, this is cytosine and thymine, sorry, CNT. And this is 160 nanometers. So when we get shorter than about 160 nanometers, this is the ionization potential. That means how probable it is that absorbing a photon is going to ionize. So if we get below 160 nanometers, we have a large ionization potential. So we're destroying these molecules. So we want to stay below this region, or actually below about 210 nanometers. So we don't have destruction. And we need the short wavelength range in the upper atmosphere, only in the upper atmosphere, to produce hydrogen cyanide and ribose. But we don't need it on the surface, because if it arrived at the surface, it would also, of course, ionize these molecules, destroy them. Okay, so let me go a little bit fast just to finish everything, because I think we're going to get thrown off in about 5 or 10 minutes. Let me just go through this in English, and then if you have any questions, if we still have time, I'll go back, okay, to these slides. So then these are the different intensities of the light, which would be on the planet at a distance which would give liquid water, because as we said, we need liquid water on the planet, or we think we need liquid water to get life like we know it on the planet. So these are the different fluxes in the graph here, and these are the fluxes which I am plotting here. And I came up with a formula. It's very rough, maybe a very approximate formula for the probability of discovering life, knowing that we need a certain amount of this long wavelength UVC light, and we need it for, in fact, 6 independent processes, okay? And so we can raise it to the 6th power, because that's how important this light would be for the process of the formation of life. Okay, but we don't want any of this medium wavelength range, so we raise it to the -m. So this goes in the denominator. And there's only really one process which is negative for this light, and that is the ionization process. So we use a factor power indice of 1 here. And also we need short wavelength light. It's good for us, but only in the upper atmosphere. So this is the process which is producing hydrogen cyanide, let's say. So we have one process here, so it goes as a factor 1 in the exponential. And so we can compare the probability of producing life on these different stars based on the concentration or the intensity of the light in these different wavelength regions raised to these powers, which represent just how important this light is to the production of life. Okay, and we multiply that by the age of the star. One thing I haven't mentioned is that these different star types have different ages. For example, A-type stars have only 370 million years life. And that is because they are very big stars. They're very massive stars, so the temperatures are very great inside them. So the nuclear fusion processes which are occurring are very rapid. There are many types of nuclear fusion processes occurring in these A-type stars, so they have very short lifetimes, only 370 million years. F-type star has about 3 billion years, and G-type stars like our sun have on average about 5 billion years, but it depends on the type of G-type star, because, you know, there are many types of G-type stars. Ours is type 5, but they have an average life of about 5 billion years. Our star now has about 5 billion years of lifetime, but it's only at its midlife. Its full life could be about 10 billion years. K-type stars have 10 billion years, and M-type stars have beyond 10 billion years, greater than 10 billion years of life. So these M-type stars, in fact, have a larger life than the age of the universe, can have a larger life than the age of the universe. Well, so far, the age of the universe. Okay, so what I've done then is plotted the probabilities as determined by this equation, multiplied by the age of the star, and then normalized to 1 for the sun, because we know we have life with the probability of 1 for stars which are like our sun, G-type stars. So these are the other probabilities for the other types of stars. So we see, for example, for the M-type star, the probability is 10 to the minus 18. So it's impossible that we would have life on that type of star. And for the F-type and the A-type stars, there's a very high probability. But for example, on these stars, because we have only a short lifespan of these stars, 370 million years, it's very unlikely that we would get evolution of complex life, intelligent life like our own. Because at 370 million years on Earth, we only had bacteria. So we didn't have any animals, for example. On F-type stars, maybe we could get intelligent life if we were lucky, and evolution was a little bit more rapidly towards intelligence. But probably we're only going to get intelligent life on G-type stars, which are like our sun, and maybe K-type stars. But K-type stars have a lower probability of life because of 10 to the minus 6. So they're about 1,000,000 times or 100,000 times less likely to have life than our sun would. So really, if we want to be looking for intelligent life, this kind of calculation would assume that we have to be looking at only G-type stars. We could find bacterial life on these other stars, but it's likely that life didn't have time to evolve because the star terminated. And these terminated in explosions. Now, these are much more massive than the sun, so they were most likely terminate in a supernova explosion. So if there were, even if there was intelligent life and if it hadn't moved to another planet, it would have been destroyed by the supernova explosion very quickly. So we should be looking at only G-type stars and maybe K-type stars. But there would be very small probability because we don't get very much long wavelength UVC light in K-type stars. Okay, and so there's another problem with M-type stars, and I put this in because I gave this as a talk in astrophysics in astronomy in the university in UNAM. Because they have a program there which is looking at M-type stars, and I tried to emphasize that you're not going to find much life on M-type stars. And there are other problems besides the lack of UVC light. And these M-type stars don't have they have a large amount of emission of particles. And so these particles, unless the planet has a very strong deflecting magnetic shield, then these stars, because we have to be in so close to the star, remember at 0.16 astronomical units, and there's a lot of particles coming off these M-type stars, more than comes off G-type stars, these particles are going to destroy the atmosphere. So without an atmosphere, we won't have protection, from the particles. And so we're very unlikely to have life on these M-type stars. And also, we need liquid water on these stars. So as I said, we have to be in closer than 0.2 astronomical units. And if we're in that close, then we're almost like the moon and the Earth. So we're at much greater distance than the moon and the Earth. But compared to the size of the planet, if it's an Earth-like planet, it would be like the moon and the Earth. And so we would get tidal locking between the planet and the sun. So that means that we would have only one face of the planet facing the sun. So that one face facing the planet would get hotter and the night side would be very cold. So it would also be hard to imagine that we could have liquid water for an extended period of time because only on the sun-facing side would we have liquid water. We won't have night or day, so we wouldn't have this UV-TAR replication process occurring. Okay, so M-type stars have these great fluctuations in temperature because the intensity also fluctuates, not only in particles, but also in light. So that would, if we had a form with little atmosphere and facing the star, we would get a very large fluctuations in temperature with the star on the planet. So that would be very unlikely that we would have life occurring. Okay, so that was some of the other reasons why we didn't have, we should not be wasting our time looking at M-type stars for life. Okay, now we have a little bit of time if anybody wants to go back to these previous slides, if they have any questions before they throw us off. And in this case, when they throw us off, then we'll finish for today. And we have only one more lecture, which is next week, Thursday. And I'll let you answer. We'll leave that lecture open for any questions, okay? So it'll be for you to prepare your questions so I can try to answer on anything that we've studied or looked at in the course so far.